Welcome back to 40 Days of Chemistry Part 9. This time we're looking at the first part of 9.3.4, Acid History. And the first science we look at is Lavoisier, but before that, in ancient times, acidus meant sour. That was the first definition, I suppose, of an acid. Alkali meant heated ashes, which were basic chemicals. But Lavoisier had the first chemical definition of an acid, and he said acids contain oxygen based on his chemical experiments. So it was the first composition-based definition of an acid. He inspired further research, but his theory had no definition of a base, and Davy later disproved the fact that acids contain oxygen. Lavoisier, for the record, had his head chopped off in the French Revolution, and that was the end of Lavoisier's contribution to chemistry. So moving along to Davy. Now Davy is the same scientist we study in electrolysis. He was the man who used the voltaic pile to perform electrolysis experiments, and using those electrolysis experiments he showed that hydrochloric acid had no oxygen, therefore disproving Lavoisier's theory. He had a new definition though: acids contain replaceable hydrogen, and bases react with acids to produce salt and water. So he improved our understanding of acid composition. He realised it was to do with hydrogen, was the important element to do with acids, and he also had the first definition of a base. But some hydrogen-containing chemicals were not acids, and there was no reason why they weren't acids, and his base definition did not relate to composition. It was just it related bases to their reactions with acids, as opposed to the actual composition of bases themselves. Next came Arrhenius. Now Arrhenius recognised that acids conduct electricity and they produce hydrogen gas in reactions. So he said acids must ionise in water to produce hydrogen ions, and bases ionise in water to produce hydroxide ions. And he also had the first idea about strong and weak acids and bases. So strong acids had 100% ionisation and weak acids less than 100%. So the good points about his theory was it explained that only some hydrogen-containing compounds, or those hydrogen containing compounds that could ionise in water or acids. It was the first composition-based definition of a base. He explained the strength of acids based on ionisation, and his theories led to the development of pH to describe acids. Arrhenius himself didn't come up with pH, but it was developed from his theories. But the downsides of Arrhenius' model, and the reason why I've chosen these particular 4 downsides, is because these are the ones that Bronsted-Lowry actually explained, so it's a nice easy way to link them together. It only applied to aqueous solutions. It couldn't explain bases that had no hydroxide ions in their composition. It couldn't explain non-neutral salts, and also couldn't explain amphoteric compounds. And that leads into Bronsted-Lowry theory. Now, Bronsted-Lowry theory is basically the idea that acids were proton donors and bases were proton acceptors, and neutralization was a proton transfer from an acid to a base. So the big positives of their theory were that they recognised the importance of the solvent in determining the acid-base characteristics of a substance. What that means is a substance will be an acid in a certain solvent if it could donate a proton to that solvent. So for example, hydrochloric acid is an acid in water because it can donate protons to water. And because it had this theory, this whole idea, the fact that it wasn't just water that acids were in, it was any sort of solvent, it explained non-aqueous acid-base behaviour. So some things could be acids in other solvents if they could donate protons to those solvents. It explained how bases could exist that didn't have any hydroxide ions themselves. For example, ammonia. A base is a proton acceptor according to them, and when it reacts with water, it accepts a proton from water and therefore produces hydroxide ions. So it has no hydroxide ions of its own, but it does produce hydroxide ions in water. It explained how some salts could be non-neutral via conjugates. We'll look at that in just a minute. It also explained amphiprotic substances. Now, just as an aside, this is still part of this 9.3.4 topic. You need to know about neutralization. You need to be aware that all neutralizations are exothermic. And one of the key ideas based on Bronsted-Lowry theory is that all strong acid, strong base neutralizations boil down to the same reaction. It's hydroxide ions reacting with hydronium ions to produce water, and therefore all strong acid, strong base neutralizations have approximately the same enthalpy change of minus 57 kilojoules per mole. And the very fact that it's exothermic is one of the reasons we don't do neutralization reactions on our skin if we spill something on our skin. Moving along to what it means to be amphiprotic. Now, amphoteric substances, we learn about them in amphoteric oxides. Amphoteric substances are substances that actually react with both acids and bases. Now, Bronsted-Lowry theory explained a subset of amphoteric substances. So amphoteric is the whole class of all chemicals that react with acids and bases. They explained something called amphiprotic substances, substances that didn't just react with acids and bases, but could act as acids and bases, i.e. they could donate protons and accept protons. So an example is the bicarbonate ion, HCO3-. When you react with a strong acid, here it is, it's accepting a proton from the strong acid or from the hydronium ion, therefore it's acting as a base in this reaction. But when you put it with a strong base, the bicarbonate ion will donate a proton to the hydroxide ions from the strong base, Therefore, in this situation, it's acting as an acid. So the bicarbonate ion can act as an acid and act as a base, and therefore it's called amphiprotic. Now, one of the reasons we use this chemical for neutralization is because it's amphiprotic. It can neutralize both acids and base spills. It's also stable, it's cheap, and it's non-toxic, and therefore it's a very good chemical to use for neutralizing spills. The concept of conjugates is a very important aspect of Bronsted-Lowry theory, and it goes that when an acid donates a proton, it becomes a species with one less proton, obviously, but now that species can accept a proton, and therefore that species that it becomes is itself a base, and it's called the conjugate base of that original acid. And together that acid and that conjugate base are called a conjugate pair. Now, to illustrate that, let's look at the example of hydrochloric acid. Now, hydrochloric acid, we know, being an acid, donates protons. There it is, donating a proton to water. That water becomes the hydronium ion, and the hydrochloric acid becomes the chloride ions. This chloride ion is what the HCl has become once it's donated a proton. So we call the HCl the acid, and the chloride ion is the conjugate base. And together, the hydrochloric acid and the chloride ion are called a conjugate pair. So it's a conjugate pair there. A similar example, this time looking at a base example. Ammonia, we know, is a base. That means it accepts protons, and here is accepting protons from the water. Once it accepts a proton, it becomes a species with one more hydrogen ion, so one more hydrogen and one more positive charge. In this case, it's the ammonium ion, and that ammonium ion can, we know, donate a proton possibly back to the hydroxide ion. So that ammonium ion itself is an acid. So when a base accepts a proton, it becomes what's called the conjugate acid, and together the ammonia and the ammonium are called the conjugate pair. Now, if you look at these two equations, we know we've got different arrows in these equations. The arrow in this hydrochloric acid equation is a straight arrow, whereas this one's an equilibrium arrow. And that's because in a strong acid, every molecule in a strong acid donates at least one proton. Therefore, we give it the full arrow. It's not an equilibrium reaction. It's not a reversible reaction. And that means that even though hydrochloric acid is called an acid, and that means chloride is the conjugate base, this reaction where chloride accepts a proton and actually acts as a base, it doesn't actually happen. That's why we don't have that second arrow pointing backwards. And therefore, strong acids have very weak conjugate bases. Effectively, they're not really bases at all. They're almost like theoretical bases as opposed to real bases. However, with a weak base like ammonia, it's in equilibrium with its conjugate, and therefore both reactions happen. The ammonia will accept protons, the ammonium will donate protons, and therefore weak acids have weak conjugate bases. And that concept of weak acids having weak conjugate bases and strong acids have very weak conjugate bases is important when we start thinking about neutrality of salts. Now, salts are formed from acid-base or neutralization reactions. We know that acid plus base goes to salt plus water. We know that water is a neutral chemical, but that salt is actually formed from the conjugate acid and conjugate base of the parent acid and base. And therefore that salt's not necessarily neutral depending on the strength of those original acids and bases. So if we react a strong acid and a strong base together, we're going to have two very weak conjugates. The strong acid is going to have a very weak conjugate base, the strong base is going to have a very weak conjugate acid, and that means that salt is going to be neutral. Something like sodium chloride, we know, made from reacting hydrochloric acid and sodium hydroxide, will be a neutral salt. But if we have a strong acid and a weak base reacting together, the strong acid is going to have a very weak conjugate base, basically neutral, but that weak base is going to have a weak conjugate acid. So that salt's going to contain a weak conjugate acid, and therefore that salt's going to be slightly acidic. And an example of that's reacting ammonia with hydrochloric acid to produce ammonium chloride. That ammonium chloride will dissolve in water to produce ammonium ions and chloride ions. Those chloride ions are the very weak conjugate base of hydrochloric acid, which so they're basically neutral. But that ammonium ion is the weak conjugate acid of ammonia. And therefore that ammonium ion can donate protons to water to produce hydronium ions. And therefore that ammonium ion is acidic. And therefore that ammonium chloride salt is an acidic salt. A similar situation happens if you mix a weak acid and a strong base in neutralization, because the weak acid is going to have a weak conjugate base, the strong base is going to have a very weak conjugate acid, so overall that salt's going to be basic. So let's look at the example of acetic acid reacting with sodium hydroxide. Now the salt we're going to produce is sodium acetate, and that acetate ion is the weak conjugate base of acetic acid. So when sodium acetate dissolves in water, it's going to produce that acetate ion, or ethanoate ion if you want to call it the ethanoate ion. And that ethanoate ion, once it's free in water, can actually accept protons from water, producing hydroxide ions. So because that sodium acetate contains that acetate ion, which is weakly basic, the whole salt is basic. Now, if you ever asked to show that a certain salt is acidic or basic, or write an equation or explain why a certain salt is acidic or basic, they might give you ammonium chloride, they might give you sodium acetate. If they ask you to explain why it's non-neutral, all you've actually got to do is write the equations out to show it acting as an acid or acting as a base. As soon as you've shown the equation showing that salt acting as an acid or base, that's it, you've explained why it's acidic or basic. If you want to, you can go back and talk about the parent acids and bases, but that's not the most important thing. The most important thing is to actually be able to write your equations down. And moving on to the last bit of this talk, this is buffers. Now, buffers are a very important part of the HSC chemistry course, mainly because to explain buffers, you've got to explain three separate chemical concepts. You've got to explain Bronsted-Lowry theory, you've got to understand the Chatelet's principle, and you've got to understand the concept of pH. So what is a buffer to start with? Well, a buffer is a mixture of approximately equal amounts of acid and its conjugate base, which form an equilibrium with hydronium ions. It's very important you say they form an equilibrium with hydronium ions. Now, because it's equilibrium, that means the Chatelet's principle applies. And by the Chatelet's principle, if you add an acid or base to this equilibrium, which would normally change the hydronium ion concentration, the equilibrium will actually shift to counteract the change and keep the hydronium ion constant, which is why it's important to say it's an equilibrium with hydronium ions, because as soon as something's in equilibrium with hydronium ions, if anything was going to change that hydronium ion concentration, we know the Chatelet's principle is going to apply to try and buffer or stop that change in hydronium ion concentration. And why is it important to say that? That links to the pH thing. pH is minus the log of the hydronium ion concentration. So because the hydronium ion concentration is kept fairly constant by the Chatelet's principle, that means the pH stays fairly constant. So the normal changes to pH that would happen if you add an acid or base are buffered, hence the name buffer. And the example we studied this year was the dihydrogen phosphate hydrogen phosphate buffer that's inside the internal fluid of your cells. And when you write the equilibrium equation down, make sure you write it down in such a way so the dihydrogen phosphate is on the left, acting as an acid, therefore producing hydronium ions. Because when you've got the equation with hydronium ions, it's very easy to talk about pH. If you try to use the other equation with hydroxide ions there, it makes it much trickier. So try and use this equation all the time. And all you've got to be able to say is if you add an acid, which means increasing the hydronium ion concentration, by the Chatelet's principle, equilibrium is going to shift to the left, which keeps the hydronium ion concentration constant, and therefore the pH constant. And similarly, that's not constant obviously, but similarly, if you add a base, that means hydronium ions are being consumed. Equilibrium is going to shift to the right to replace those hydronium ions, which means once again the hydronium ion concentration stays constant, and therefore the pH stays constant. And that pH it stays is approximately 7.2. That's what your body needs.